All right, let's talk about something I'm sure many of you have run into. You spend weeks, maybe even months on a design. The CAD model, it's perfect. The dimensions, you've checked them a million times. It gets sent off to manufacturing, then it heads to assembly, and the parts just don't fit. It's an incredibly frustrating story, and it's super common. But what if the real problem isn't the numbers on the page? What if it's the language we're using to describe them? I mean, that's the million-dollar question, right? It's the thing that keeps engineers and machinists staring at the ceiling at 3 a.m. You know you followed the drawing. They know they followed the drawing. So what gives? Where did things go wrong? Well, the answer is usually hiding in this sneaky layer of ambiguity, this gap between what the designer meant and what the manufacturer thought they meant. Take a look at this flow. Information gets passed along from design to manufacturing and then over to inspection. It's almost like a game of telephone, right? At every single handoff, there's a real chance for misinterpretation. A simple note that just says, make this surface flat. Well, how flat is flat? My version of flat might be totally different from yours. What we really need is a rock-solid system to make sure everyone is speaking the exact same language with zero room for error. And that system, that's exactly where geometric dimensioning and tolerancing, GD&T, comes in. Now look, this isn't just about throwing a bunch of complicated-looking symbols on a drawing. Not at all. It's about swapping out that expensive ambiguity for pure mathematical certainty. And why should you care? Because when design intent is crystal clear, you get less scrap, fewer delays, and way faster assembly. It's basically the rulebook for precision, and it hits the bottom line hard. This quote from NIST, the National Institute of Standards and Technology, really just nails it. It says, GD&T is a language to communicate design intent. Let's chew on that for a second. It's a language. It's a way for a designer to say, hey, look, this isn't just a picture of what the part should look like. This is about how it needs to function. And here are the exact acceptable variations that will make sure it does its job. Okay, so check this out. See that box with all the symbols? That's called a feature control frame. And if GD&T is a language, then this is a complete sentence. It's got everything. The verb, which is the geometric control, the tolerance value, the references. There is absolutely zero room for guesswork here. It's a direct, unambiguous instruction that anyone, anywhere, can understand. Well, I say anyone, anywhere, but there's a catch. And this is where things get really interesting and honestly a little complicated. Because it turns out this so-called universal language has two major and very distinct dialects. And you really need to know the difference. So on one hand, you've got ASME. That's the American Society of Mechanical Engineers. Think of this as the main standard here in the United States. Then, on the other hand, you've got ISO, the International Organization for Standardization, and that's pretty much the standard for the rest of the globe. Now, they look super similar on the surface, but lurking underneath in their default settings is a totally fundamental difference in how they think about parts. And that brings us right to the main event of this whole explainer. It's the battle of the principles, envelope versus independency. And trust me, this isn't just some boring technical jargon. We're talking about a core, fundamental disagreement about the relationship between a part's size and its actual shape. All right, let's kick things off with the ASME default. You'll hear it called Rule Number 1 or the envelope principle. It applies to something called a feature of size, which is really just the fancy way of saying anything you can measure with calipers, like the diameter of a pin or the width of a slot. Now here's the key. This rule says that feature has to have perfect form, like perfectly straight or perfectly round, when it's at its maximum material condition, or MMC. Don't let MMC scare you. All it means is the part is at its biggest, heaviest state. Think of a pin at its absolute biggest allowed diameter, or a hole at its smallest allowed diameter. So with ASME, size and form are basically handcuffed together by default. Okay, now let's flip over to the other side, the ISO default. This is called the independency principle, and it's the exact opposite of what we just talked about. By default, ISO says a part's size tolerance and its form tolerance are two totally separate things. They're independent. They have zero relationship with each other unless you go out of your way to add a specific symbol on the drawing to link them. So let's make this super clear. Let's go back to that simple pin. Under the ASME default, right, if you make that pin at its absolute biggest allowed diameter, it also has to be perfectly straight, no questions asked. Its size literally controls its form. But
Under the ISO default, that very same pin, at that same max diameter, could still be a little bent. It could have some straightness error. Why? Because size and form are treated as separate things. You see the problem? Two different standards, two potentially very different parts, all from the exact same numbers on a drawing.
So why does any of this matter? I mean, who cares about this philosophical difference when you're on the shop floor? Well, you should care. Because if you aren't specific about which language you're speaking, it can lead to some pretty big problems. I mean, just think about it for a second. Let's say you send a drawing out to a manufacturer, but you forget to specify which standard to use. What do you think happens? A shop in the US, they're going to default to the ASME envelope principle. A shop over in Germany, they're going to default to the ISO independency principle. One assumes size controls form, the other one doesn't. And right there, that is how you end up with two batches of parts that are both perfectly in spec according to the drawing, but they still won't fit together. Oh, and it gets even trickier. It's not enough to just scribble ASME in the title block and call it a day. Why? Because these standards are living, breathing documents. They evolve. The rules change over time. New symbols get added. Definitions get tweaked. I mean, the way you control a complex profile in the 2018 standard could be totally different from how you did it back in the 94 version. And that's exactly why specifying the revision year is every bit as critical as naming the standard in the first place. Okay, so let's boil this all down. What are the big things you need to take away from this? Number one, GD&T is a language, and its whole purpose is to kill ambiguity. Number two, ASME and ISO have a huge philosophical difference right at their core. Remember, ASME's default is the envelope principle. Size controls form. ISO's default is the independency principle. Size and form are totally separate. And finally, the most important thing you can do, on every single drawing, you have to specify the standard and the revision year, every single time. So I'm going to leave you with this one question to think about. I know your drawings are precise, but after everything we've talked about, are they unambiguous? Can you say with absolute certainty that there is no room for misinterpretation? Because that is the real standard that GD&T challenges all of us to meet.